Hi guys, welcome to ECE 100 Discussion 3. You'll have midterm 1 next week, and it's time to get prepared for it. In case you haven't viewed the previous discussions, you can watch them now to get a better understanding of the course materials. So the discussion 1 talks about review of chapter 1, and the 2 review chapter 2 from 2.1 to 2.6. And discussion 3, which is today's topic, will review the 2.6 to 2.8 in chapter 2, which covers Thevenin and Norton equivalent circuits, as well as superposition and Wheatstone bridge. Let's start today. The first point is Thevenin and Norton equivalent circuits. And here are the steps I summarize for you guys. The first one is to determine terminal A and B and the work area, which means the box. You're going to simplify it into only a source and a resistance. And the second step is to temporarily make A and B open circuit, and then calculate the voltage between A and B, the voltage of the open circuit, which is basically VT, the Thevenin voltage. And the third step is to temporarily make A and B short circuits and calculate the current flowing through it, which is basically IN, the Norton current. And step 4 is to calculate the equivalent resistance between A and B from the outside, looking into the work area. And because of the relationship between IN, RT, and VT, as long as you get 2 of these 3 variables, you will be able to get the other one. So among step 2, 3, and 4, you can choose 2 of them. Okay, so if you want to directly calculate the resistance instead of using the VT over IM to get it, what you can do is to zero all the sources, calculate the RT from outside looking into AB. And the last step is to draw the Thevenin or Norton equivalent circuit, which means you should turn this circuit into the equivalent circuit. Let's take Thevenin, for example. This is VT, this is RT, and then you should put it back to where it was. For example, if the AB were connected to a load before, now you should connect the equivalent circuits to the load in the same way. Okay, so here's a quick review of the steps about how to calculate the equivalent circuits. But there are a few things we need to be very careful about, which are in the notes section here. The first one is what we mentioned just now. You only need to choose 2 from the step 2, 3, and 4. And the second thing to take notice of is the word temporarily, which means that you make A and B open circuit or a short circuit only because you want to calculate the VOC or ISC. So after you get the results, after you calculate them, you get the values, you should return to the original circuits, which means that the A and B should be connected to where they are. Okay? It doesn't mean that you permanently remove the things between A and B, or it doesn't mean you permanently connect A and B directly. Okay? And the third point is about the work area. So one thing you must pay attention to is we cannot. So we may have controlled sources in the work area, but the controlling variable must be inside the work area. This is to say, if there is a controlled source in your circuit and the controlling variable is outside this part, that means that this circuit cannot be converted into the Thevenin equivalent circuit or Norton equivalent circuit. Okay, so make sure there's no controlling variables outside the working area. And the next one, be careful about the step 4. So only when there is no dependent source in the work area can you zero in the sources. So in other words, when there are only independent sources in the work area, you can use the step 4 technique to zero in the sources and calculate the equivalent resistance. Okay? Otherwise, you have to choose step 2 and step 3. And the last one to pay attention to is, what is the definition of looking into AB? I don't get it. So it is a little bit tricky. So for example, if your circuit looks something like this, and A and B are on the same side, and the circuit is on the other side, and it will be easy for you to tell. Looking into AB means, for example, here from the right, and the equivalent resistance should look like this, right? But sometimes the circuit is a little bit different. For example, what if the AB is in the middle, right? So in this case, you need to be careful. You need to check that the question is asking, for example, the left-hand side of the AB terminal, or they are asking all the rest. If they are asking, they are asking only the left of the terminals A and B, the things will be easier. You just need to remove the right-hand side part, and then just solve it just as a previous example. But if they are asking about all the rest, it will be easier to understand if you redraw it in this way. So A can be extended. So what they are asking is actually this work area. Okay? Does it make sense? Great. So or these concepts and tips about the Thevenin and Norton equivalent circuits may seem a little bit abstract. So let's come to the Wheatstone's bridge and follow the steps as an example. So Wheatstone bridge is a circuit used to measure unknown resistance. And when its 4 resistances are in a specific ratio, the requirement is satisfied and the bridge will be balanced. And then we can derive the unknown resistance using the other known resistance values. Okay? So now let's take it as an example to see how to analyze the equivalent circuit step by step. According to our guideline just now, the first step should be determine the terminal A and B. And here, I choose these 2 points as A and B because what I care is about the reading of the detector. Okay? So I don't care about the rest of the circuits. I want to redraw it as an equivalent circuits to simplify my analysis. Okay? So I choose these 2 points. And then, to make it clearer, I redraw the node A and B to put them on the right, and all the things left I put in the work area. And we are going to focused on the work area, okay? And you'll see that the detector is still connected between node A and B. Now to do some quantitative analysis, suppose we know the values of all the resistances. R1 is 1 ohms, R3 is 2 ohms, R2 is 2 ohms too, and R4 is 3 ohms, okay? And the step 2, calculate the VOC. So let's make AB an open circuit. What should we do now? Yes, we should remove the detector here because we are assuming that it is an open circuit temporarily. And then how can we get the VOC? So VOC here is basically the voltage across A and B when it is open, right? We can use all the methods we learned, like voltage current division, node voltage analysis, or mesh current analysis if you can draw it in a planar fashion. So here I will use the voltage division because that is already enough to solve the problem. Okay, let's assume we know Vs2. Vs is 10 volt here. Okay, perfect. Following the loop, going through Vs, R1 and R3 here, and do KVL. We'll have minus Vs times I1 R1 times I3 R3 equals to 0, right? A and B is open now, so the IG equals to 0, so I1 equals to I3. I1 equals to 3, so R1 plus R3 times I1 equals to 0, right? And the voltage across R3, let's name it V3, okay? The V3 equals to I3 times R3 equals to I1 times R3 equals to I3 divided by R1 and R3 times. Great. And then similarly we can get V4 equals to R4 over R2 plus R4 times Vs, following the outer loop, right? And we'll notice that V3 is equal to, and V4 is equal to VB. Thus, we know that VAB equals to VA minus VB, following the reference polarities in the circuit. Congratulations, you get the open circuit voltage here. Next, let's come to the calculation of short circuit current, the ISC. Okay, so by shortage A and B, we can draw a circuit like this, right? And to simplify it, let me draw it in this way. Okay, this is I1, this is I3, this is ISC, and this will be I2, this will be I4, right? And let's use node voltage. Oh, sorry. And one thing to know that even A and B are equivalent because they are on the same ideal conductor, but because you try to compute the current flowing on the conductor, right? So you can't merge them into one point, okay? That is a tricky trap. Let's just keep A and B separate and use the negative polarity of the voltage source as reference node. And this is V1, is node 1. This is node A. This is node B, right? We're done. For V1, we directly get its value, so we don't need to write the KCL function for it. And for node A, the currents flowing in is equals to currents flowing out, right? And let's substitute the current variable with our node voltage. And because a current is flowing into it, there's a minus here, it is equal to ISC VA over R3, right? And for node B, current flowing in, flowing out. I2 E1 minus, right? And we already know equals to 10 volts. We get V1 equals to 10. And remember, we don't have resistance between A and B, so their voltage, right? There's no voltage drop over the A and B equation here. Thus, we have 3 unknowns and 3 independent equations. Further simplified. Okay, so we get our short circuit current 0.357 A. By dividing VT with IN, we get 1.8. But in this circuit, we observe that there are no dependent sources, right? There is only one voltage source here. So we can use the zeroing method to calculate the RT directly. Looking from outside into the work area from terminals A and B, this equivalent resistance is what we want. And how to zero all the sources? That means make their values equal to 0. For a current source, when the value is 0 volt, it becomes an ideal conductor, right? Which is short circuit here. And when a current source equals to 0, which means no current is flowing through it, it is basically an open circuit, right? And as you see here, what should we do? Yeah, by zeroing the voltage source, we are connecting it with a wire directly, right? And what is the result? Yes, if we name this node as 3 and this node as 4, we'll see that after we zero the source, 3 and 4 are equivalent now, right? So let's repeat the analysis about the resistance relationship again. Okay, so R1 is between 3 and A, R2 is between 3 and B, R3 is between 4 and A, and R4 is between 4 and B. Excellent. But now A is not equal to B because we are not assuming A and B is a form a short circuit, right? So now the resistance relationship changed to R1 and R3 are in, and R2, R4 are in parallel, right? Okay, so now we need to read R1 by merging the things in the blue box. You'll get that the equivalent resistance, the parallel resistance on the left, parallel sum of resistance on the right. So great. Yes. And that is how we get the equivalent resistance. Let's substitute the values to check if it is the same as the other method. Okay, so R1 is 1, 3 is 2, R2 is 2, and R4. It's the same as the equivalent resistance we directly compute, right? And there may exist some approximation error. Great. In conclusion, RT, VT, and IN. Calculate 2 of them and get the other one with VT equals to IN times RT. And then redraw your circuit into its equivalent ones, as shown below. Okay. Now let's come to superposition. Superposition means the total response, RT, is equal to sum of Ri, the sum of individual response caused by independent sources only. So what is the definition of response? That means the voltage or current of an element driven by a source, an independent source. And what do we mean by zeroing a source? Make a current source open circuit and make a voltage source short circuit. And superposition principle only applies to linear circuit, which means that it only consists of linear elements like resistance, and we'll cover in the future the inductor and capacitor, as well as independent sources. And controlled sources are also allowed, but make sure that they are linear controlled sources. What is linear controlled sources? Let's see this example. Suppose we have a controlled source, controlled voltage source, current controlled voltage source, equals to K, a constant, times the square of Ix, which is a controlling variable. Is it a linear controlled? No, because it corresponds to the squares of the controlling variable. And what about this? V equals to K squared Ix. This is a linear controlled sources because K is a constant and K squared 100 is also a constant. So V is proportional to the controlling variable Ix. That is to say, this is a linear dependent source. Okay, so best luck with your midterm 1 and welcome to my office hour before the exam. Thank you. Goodbye.